All right, in this part, we're going to take a look at the Westergaard function. Just for historical reference, Westergaard was an elastician, and he was hired at the University of Illinois at Urbana-Champaign in the Theoretical and Applied Mechanics department. He was the department head there. And this would have been, I guess, in the 1800s, mid to late 1800s. And the story goes, at the time, a little bit later, after he had been hired, Illinois had a chance to hire Stephen Timoshenko. He's a very famous elastician. Westergaard's fairly famous, but you could arguably say that Timoshenko was probably much more famous than Westergaard. But Illinois declined to hire Timoshenko, as the story goes, because they already had someone working in elasticity. Well, what Westergaard is known for is coming up with this Westergaard approach, this function of complex stress potentials. He did lots of other things there in the area of elasticity, but probably he's best known for this complex potential approach for crack problems. So we're going to talk about this in a little bit of detail in general terms, and then we're going to look at a particular function that satisfies Cauchy-Riemann equations, the biharmonic equation, and the boundary conditions for a cracked plate. And Theoretical and Applied Mechanics department is my alma mater at UIUC. It's where I got my master's and PhD in mechanics. Now, as I write this stuff down, I'm going to have big Z's and little z's. And I'll try to make my big Z's have these little tails on them, these little hooks, so that we know that it is a big Z. And I'll try to make my little z's look small. But admittedly, things could get confusing, but I'll try to do the best I can. All right, so consider a complex function, capital Z, of Z, that satisfies the Cauchy-Riemann equations. And this is a classic approach. It's in Anderson and some other books. And so we're going to go through this approach. And it's a little bit twisty. And for notational convenience, we're going to define some terms. Now, if we want the derivative, and notice these are straight derivatives, of some function z double bar, we're going to call that z bar. Okay, so this z bar is the derivative of that function z double bar. We're going to define the derivative of, it's a straight derivative. I have to be really careful here since I've been doing a lot of partial derivatives. We're going to define the straight derivative of that function z bar as z, and we're going to define the derivative of that function z as capital Z prime. All right. So these are just ways to show different orders of derivatives. Now, something that we have to be really careful about now is that if you have dealt with complex numbers in the past, you may have dealt with something called a complex conjugate. And you represent a complex conjugate with a bar over a complex number. This is not what we're talking about in this case. The bar does not represent a complex conjugate. All right, so just to say that again, the bar does not denote a complex conjugate. All right, so let's get down to the Westergaard function. Now, the traditional way is to write this with the symbol psi. And the function is psi is the real part of some function z double bar plus y times the imaginary part of z bar. And it is a complex Airy stress function. Now, as an Airy stress function, then we can find these stress fields from partial derivatives, and instead of using the symbols phi that we had talked about previously, we're going to use the symbol psi now because we're talking specifically about the Westergaard function. But whether phi or psi, sigma x is the second partial of psi with respect to y twice. Stress field sigma y is the second partial of psi with respect to x twice. And either tau xy, or you can call it sigma xy, is the negative of the second partial of psi with respect to x and y. So what we're going to do first is we're going to determine general expressions for these stress fields in terms of that particular Westergaard function. Now we're going to need second derivatives, but we got to start with the first derivative. So let's start with looking at our sigma x, which is the second partial of psi with respect to y twice. It's hard to draw straight on this thing. I'm going to start with the first derivative of psi with respect to y. Now, since this is a complex function, we're going to have a real and imaginary part. Let's write down what psi is up here so we don't have to flip back to the previous page. Remember we said psi was the real part of z double bar plus y times the imaginary part of z bar. So, partial derivative of psi with respect to y would be the partial derivative of the real part of z double bar with respect to y. And since we have y times the imaginary part of z bar for the second part of psi, we're going to have to use the product rule. And so the derivative, partial derivative of y with respect to y is 1. So we're going to have the imaginary part of z bar plus y times the partial derivative of the imaginary part of z bar with respect to y. All right. Now, let's see if I can find the right page here. Okay, I'll write this out to the side. One of the things we need to recall is the partial derivative of, with respect to y, of the real part of a function. The negative of that is equal to the imaginary part of the derivative of the function. So let's see what we have. If you notice, that first term is the partial derivative of the real part of z double bar. So what goes in here now is the imaginary part of the derivative but with a negative sign thrown in. Okay, and here we have the imaginary part of z bar, and then we have plus y times, all right, now here, again, we're going to have to look up the Cauchy-Riemann equation. We have the partial derivative of the imaginary part with respect to y. And that's equal to the real part of the derivative. All right, so what goes here then will be y times the real part of the derivative of z bar with respect to z. One more time, we're going to write this down. Partial of psi with respect to y is negative of the imaginary part is negative imaginary of the derivative dz double bar with respect to z. But from our previous page, for the notational convenience, we're saying that d, that's capital Z double bar with respect to little z, is equal to z bar. All right. So this becomes capital Z bar. Okay. And so these terms will annihilate each other. Okay, and so what we're left with is that the first derivative of psi with respect to y is y times the real part. And again, for notational convenience, we made a substitution here. The derivative of capital Z bar with respect to z is going to be equal to the function z. All right, so that's the first derivative. Okay. So I mentioned it gets a little bit twisty, so kind of hang with me and flip back at those notes. Now what we need, though, is the second derivative of psi with respect to y twice. So we have this term, and it's a product term, so we're going to have the first times the partial derivative of the second term with respect to y, plus the derivative of the first, which is 1, times the second term. Right now, we have the partial derivative of the real part of a function with respect to y. That's equal to the imaginary part of the derivative of the function. So that, in this case, with using the notational convenience again, would be imaginary part of z prime plus, here, the real part of z. So what this says then is that the stress field sigma x is going to be equal to, let's write it this way, the real part of the function z minus y times the imaginary part of z prime. Now, without going through the details here, and usually I leave this as a homework problem, we can figure out the stress field in the y direction. Turns out it's the real part of capital Z plus y times the imaginary part of the derivative, z prime, and tau xy is minus y times the real part of z prime. So if we can find a function z, we can take its derivative, and then we can find the stress fields. Now, for completeness, let me go ahead and write down sigma x on this page as well. And make a note that we just need to find the right z. And we get all these stress fields for our particular problem. All right. Well, let's write down the Westergaard function one more time. Let's talk about it just in general terms again, too, before we get into the specific function for z. We started out with this thing. And then we took the derivatives and we got to those stress fields. Now, I think it probably took Westergaard quite some bit of time to figure this all out. And we are the beneficiaries of his hard work and persistence. Now, exactly what his thought process was to figure this out, I can't really tell you. What I always joke about in class is that, you know, in the 1800s, he didn't have cable TV, Super Bowl Sunday, you name it, the internet, Facebook to mess with. He had a lot of time to think about things, and I think he put that to good use for this particular kind of problem. So area stress functions really aren't, you don't really see any new ones these days to speak of, but it takes great insight into the particular problem. So now let's take a look at a specific function z that will work for our crack problem. All right, so specific z that we're going to look at, capital Z, is sigma times little z, square root of z squared minus a squared, where little z is x plus iy. And what we're proposing here is that this is a solution to a crack in a biaxial stress field of an infinite plate. So we have some infinite plate here. I'm trying to draw these edges a little jaggy. And on both directions, we have the stress field sigma. And the crack, we're going to center in our coordinate system, which is x and y. And the crack, I'll kind of draw this way, as if it's opened up, will be a crack of length 2a. So that from the origin it extends a distance a to the right and a distance a to the left. All right. Now, if we look at this function, it's analytic, except for a certain region. So what I mean by analytic is it will give us real numbers, and it won't cause issues except for a certain region. And that region is in between plus and minus a on y is equal to 0. And if we were to look at this function, capital Z on y is equal to 0, what we would get would be sigma times x times the square root of x squared minus a squared. Of course, if x is less than a, then we have this square root of a negative number. And I guess I can put the magnitude symbol here. If the magnitude of x is less than or equal to a, then z is imaginary or complex, with the real part equal to 0. All right, now remember what our general stress field equation said with our Westergaard function. Sigma x is the real part of capital Z minus y times the imaginary part of z prime. What does this tell us? On y is equal to 0, this imaginary part term goes away, and there is no real part, so that tells us that the stress sigma x is equal to 0. Sigma y says that the real part of z plus y times the imaginary part of z prime, but by the same reasoning, that would have to be equal to 0 once we're on that crack face. And then with tau xy being equal to minus y times the real part of z prime, then again, since y is equal to 0, that is equal to 0. So the crack is traction free on y is equal to 0 between plus and minus a. All right, so what that's saying is that when the crack is open, you cannot transmit any stress through those faces. They're not touching. So we can't get any stress being transmitted, and that's what we want. That's a good thing. That's our boundary condition. And then if we look at the other extreme, when the magnitude of little z approaches infinity, then what we'll get, if we go through the details, is that both sigma x and sigma y will be equal to sigma, and tau xy will be equal to 0. So the boundary conditions are satisfied. So we're reasonably comfortable that this specific capital Z function, sigma little z divided by the square root of z squared minus a squared, is a good solution to this particular problem that we're trying to examine. All right, let's get into the details now with the stress fields. All right, and we're going to look in the plate a little bit, and we're going to look somewhere outside of the crack tip. And the point we're going to look at is, we're going to call that Z star, which is Z minus A. And in this case, then our capital Z would be analytic, and it would be sigma little z square root of z squared minus a squared. And it's just going to be more convenient if we look at y is equal to 0. And on y is equal to 0, then capital Z is sigma x That's a sigma times an x. And we have the square root of x squared minus a squared on the bottom. All right, let's draw the crack. Our origin is in the middle of the crack. That way is our x direction. So a point out in front of the crack on the plane y is equal to 0 will get us to the distance x. And the length from the origin to the tip of the crack on the right is the distance a. So we can also define an x star distance as x minus a, all right, which would be the distance from the crack tip. So the distance from the origin, the distance from the crack tip to that same point would be x star. Let me get my figure looking good here. All right, so x star would be the distance x minus a. Or if I want to put this in a different way, I can say the distance x would be the distance x star plus the crack tip distance a. All right, so now we're going to shift things to the crack tip. We're still looking on y is equal to 0, so let's look at this function where we have sigma times x, but now x is equal to x star plus a. And on the bottom, we have x squared, which we can expand as x star squared plus 2ax star plus a squared minus a squared on the bottom. All right, which we can simplify a little bit. Which we can factor out an x star from these terms. So we'll have sigma x star plus a. We have the square root of x star, and we'll have a square root of x star plus 2a. Now, if we're very near the crack tip, and we're not, and in particular, if x star is much less than the length of the crack, okay, then on top, we'll have sigma a, and on the bottom, we're going to have the square root of 2 and x star. So the first term here is just the square root of x star, and on the bottom term, if x star is much less than a, then on the bottom we're going to have a square root of 2a on the bottom, which we can simplify one more time. Write it this way: we're going to have sigma square root a divided by square root of 2 and the square root of x star. All right. Now, on y is equal to 0, we know that sigma x and sigma y are both going to be equal to the real part of capital Z. And since this is all real, the real part of capital Z, then is going to be sigma square root A over square root of 2 square root of x star. Now if we look at this x star is the distance away from the crack tip. As we approach the tip of the crack, where x star goes to 0, all right, then the stresses are going to go to infinity. And it goes to infinity in a particular way. It goes to the infinity by the square root of distance singularity. So sometimes people say that a crack tip stress field has a square root r singularity. This is what they're talking about. Now the coefficient of that 1 over square root of x star is known as the strength of the singularity. So the strength of the singularity is sigma square root A divided by the square root of 2. Okay, let's write that on the next page. So this is the strength of the singularity. And for notational convenience, this is expressed in a different way. The strength of the singularity is also expressed in this way. What's known as a mode 1 stress intensity, K. It's a factor we'll talk about in great detail for different cracks. Divided by the square root of 2 pi. So if we set these equal to each other, we can find an expression for the stress intensity in this particular case. We can say that K1 is equal to sigma square root pi A. The square root of 2 just cancel out on both sides. Now, what this means for us then is that for the plate with a hole, we can define a term called the mode 1 stress intensity factor. That is determined by basically two quantities. The stress in the body, the remote stress, sigma, and that makes a lot of sense. If you double the stress, you think that it's going to be a more severe stress intensity, and it is. It goes linear with that. But something that's a little bit unusual that comes out of this is that the flaw size A, which is our half crack length, is in there, but it's the square root of A. So you can have different combinations of cracks that have the same stress intensity. They'd have different combinations of remote stress and crack length. If you have a bigger crack in your structure, you can have a smaller stress and have the same stress intensity. If you have a small crack in your structure, you have to have a bigger stress in order to have the same stress intensity. But again, it goes by the square root of that crack length parameter. Now we approach this by looking at y is equal to 0, but we can have a more general approach to it. More generally, we can have this capital Z function of a particular Z star, which is again shifted to the crack tip as our origin of K1 over the square root of 2 pi Z star. Again, where little z star is equal to z minus a. All right, let's make a next part to this video series. We're going to take a look at the stress fields and polar coordinates.